In real analysis and in many other places, we know few techniques of how to find the limit of a sequence. But how to find if we have an integral that depends on a quantity like n or k, and what happens when n or k goes to infinity? What happens to the integral? So that's a very common question that we can ask. So today we are going to demonstrate this. Now, when we have a kind of sequence involving integrals or sequence of functions involving integrals, we are interested to see how the integral of a sequence of function goes, or whether it converges or not, under what condition it converges. And we know that in this domain two very extremely useful and important theorems we already know. They are known as monotone convergence theorem and dominated convergence theorem, or rather Lebesgue dominated convergence theorem. Of course, each of them has a few interesting features of their own, as for example the conditions under which monotone convergence theorem holds and slightly differ from the conditions under which Lebesgue dominated convergence theorem holds. So basically this gives us a wide range of applications, like under certain conditions we can apply monotone convergence theorem, whereas under certain condition we can apply dominated convergence theorem. And we also discussed one problem based on that deals with the convergence of measurable functions. Convergence mainly means LP convergence we mean. So today we are going to demonstrate these important theorems to some specific problems, specific functions, a sequence of functions and eventually integrals and their convergence to where they are actually converging. So we are going to discuss this thing using or demonstrate using some specific problems. So now we are going to discuss 3 to 4 problems on mostly few convergence theorems, namely a problem on monotone convergence theorem, or using problems that will use dominated convergence theorem, and also convergence of some measurable functions. The most important to note that the technique that would be used in evaluating in solving these problems. So the first problem goes like this. It's a very simple looking problem. We have to find the limit n goes to infinity integration over 0 to n closed interval. The integrand is 1 plus x by n whole to the power n into e to the power minus pi x dx. So when we are going to find the limit, let us first consider the behavior, or now just to check or see what is the behavior of the function that is being represented as integrand. First, let us write this entire integral using an indicator function. That means we can write the given integral, which is limit n goes to infinity. Limit will always be there. So integral over 0 to n closed interval of 1 plus x by n whole to the power n into e to the power minus pi x dx. We can write this as the integral over 0 to infinity closed interval. 0 to infinity, 0 part is closed, and 1 plus x by n whole to the power n e to the power minus pi x. I of 0 to n closed dx. We can always write in that way. Now, let us observe that 1 plus x by n whole to the power n, this goes to e to the power x as n goes to infinity, but more importantly, this actually increases to e to the power x. That means we can immediately have the integrand, that is 1 plus x by n whole to the power n e to the power minus pi x goes to e to the power x minus pi x as n goes to infinity, that is e to the power minus of pi minus 1 into x as n goes to infinity. So this is a result that we need to remember throughout this problem. That means first, instead of going to the integral, we have applied two techniques. One is how to write the integral using an integrated function and make the range free of n. Another thing is that just instead of looking at the entire thing, just look at the function of the integrand and see how it behaves as n goes to infinity as a function of x. So x is a pointwise. Now we apply, since this is increasing, that means monotone, that means that basically the integrand is monotone. So we can immediately apply monotone convergence theorem because all the conditions are satisfied. So we get limit n goes to infinity, integration over 0 to infinity 1 plus x by n whole to the power n e to the power minus pi x dx equals to integration over 0 to infinity e to the power minus pi minus 1 x dx. We have already seen it, and just a simple integration will give us the value 1 by pi minus 1. So this is a direct application of monotone convergence theorem. All we need to check whether the function or the integrand is monotone, and we have written this integral using the indicator function. That's the only thing that we need. So there is an indicator function involved in it. So now we can immediately write that the value of the required limit is 1 by pi minus 1. So that's the answer. Let us consider a similar type of problem, another one. So let us try to find out limit k goes to infinity 0 to integration 0 to infinity dx by 1 plus x by k whole to the power k into kth root of x. So this is slightly complicated than the previous one, because here in the denominator we have x to the power 1 by k. But again, we should proceed similarly as in the previous problem. So observe that for all x greater than 0, we immediately have limit as k goes to infinity 1 by 1 plus x by n to the power k into kth root of x is nothing but 1 by e to the power x into 1, because we know 1 plus x by k whole to the power k goes to e to the power x as k goes to infinity, and kth root of x, that is x to the power 1 by k, goes to 1 as k goes to infinity. So this entire thing is nothing but e to the power minus x, but for every x, that means it is pointwise convergence. So now we know the behavior of this thing, the limit exists, and let us also observe another thing, that as we know 1 plus x by k whole to the power k goes to e to the power x, that is increases to go e to the power x, so this is monotone. And also for all k we can observe, we can see immediately that the integrand, that is 1 by 1 plus x by k whole to the power k into kth root of x, that is x to the power 1 by k, is less than equals to 1 by 1 plus x by 2 whole square. This can be shown very easily. That means it is bounded by a function, and this right hand side function is also integrable. That's the important point to observe. So that means this integrand, the given function, is dominated by another function which is also integrable. So that immediately tells us that probably dominated convergence theorem can be of great help in evaluating this problem, or in solving this problem. So that's what it is exactly. That is, this indicates that the integrand is bounded by a function which is 1 by 1 plus x by 2 whole square, which is also integrable in the range 0 to infinity. So just apply Lebesgue dominated convergence theorem. So limit k goes to infinity 0 to integration 0 to infinity dx by 1 plus x by k whole to the power k into kth root of x, which is equals to, as we have already seen, the limit of this integral is e to the power minus x, and naturally, so by Lebesgue dominated convergence theorem we can take this limit inside the integration. So this integrand becomes e to the power minus x as the limit. So integration of that quantity, integration over 0 to infinity dx, is nothing but 1. So the value is in fact 1. But although the function is little bit complicated looking, but just application of dominated convergence theorem, or rather Lebesgue dominated convergence theorem, after checking all the conditions, because all the conditions are being satisfied here, so we get the limit as a simple value, that is 1. Now next one, and if I want to find out the limit n goes to infinity integration 0 to infinity n sin x by n divided by x into 1 plus x square dx. So this is the first time we are actually in this series of problems. This is the first time we are using kind of trigonometric functions, and let's see whether we can evaluate this integral, which is a function, the integrand is a function of, is a trigonometric function. So we will follow exactly the same way. So for every x greater than 0, we see pointwise the behavior of this function, and we know that limit n goes to infinity sine of x by n divided by x by n equals to 1, and this means limit n goes to infinity n sine x by n by x into 1 plus x square, because in the denominator this x we can write x by n, and we can bring this n from the numerator in the denominator, x by n, and 1 plus x square is free from n. So when you take the limit, the limit becomes limit will be applicable only on the part x sin x by n divided by x by n, which is in fact 1. So ultimately the limit becomes 1 by 1 plus x square, but pointwise for every x. Next, since it's a trigonometric function and in fact it's a sine function, so we know that for all theta greater than equals to 0, because actually x is positive, so for all theta greater than equals to 0, sine theta is less than equals to theta. This is very interesting. It's a very simple property. We have always observed it, but now we are going to apply this simple property of sine curve or sine theta function. So we have n sin x by n by x into 1 plus x square is less than equals to 1 by 1 plus x square, because we replace sin x by n by less than equals to x by n, then x by n and n by x cancels each other. We are left with only 1 by 1 plus x square. So that now this integrand is again dominated by a function 1 by 1 plus x square, which is again integrable over the range 0 to infinity. So again we apply Lebesgue dominated convergence theorem to get, that is, limit n goes to infinity, integration 0 to infinity n sin x by n by x into 1 plus x square dx, which is equals to, because now we can take, due to Lebesgue dominated convergence theorem, we can take this limit inside the integral sign, and which is equals to integration 0 to infinity 1 by 1 plus x square dx, which is equals to tan inverse x 0 to infinity equals to pi by 2. So that completes the result or the solution. The ultimate value is pi by 2. So now consider another one. This is the last problem that we are going to discuss today. Let a sequence of functions fn that belongs to LP space over 0 1 closed interval, and another function f belongs to LP over 0 1. For p belongs to 1 to infinity, one side is closed. That means p can be taken value 1. Also suppose that fn converges to f almost everywhere. Then show that fn converges to f in LP 0 1 if and only if pth norm of fn converges to pth norm of f. Now only part is very easy. Using triangle inequality we can immediately have modulus of norm of, whenever I say norm, it is pth norm. So norm of fn minus norm of f is less than equals to norm of fn minus f, which is very easy to see by triangle inequality. And hence since we know that fn only part means we have given that fn converges to f almost everywhere, we immediately have norm of fn minus f goes to 0, implying that since this modulus thing, this entire quantity will go to, and the right side goes to 0, so immediately have that norm of fn, that is pth norm of fn, goes to pth norm of f. So that completes the proof of only part. Now we are moving on to the more difficult part, which is the if part. And first we shall prove it for p equals to 1, which is actually relatively easy solution. We will see. It's not really that difficult, but we can think over it. Again we apply triangle inequality to get modulus of mod of fn minus f less than equals to mod of f, because p is 1. So norm and mod, they are basically same. And noting that f belongs to L1, p is 1, L1 over 0 1 closed interval, and then we apply Lebesgue dominated convergence theorem, and we get integration mod of fn d mu minus integration mod of fn minus f d mu. And it is easy to simplifying this to integration of mod of fn minus mod fn minus f d mu, and that naturally goes to mod of integration, that entire thing converges to integration mod f d mu as n goes to infinity. So this is again from this triangle inequality. Now since we know that integration mod fn minus f d mu goes to 0, therefore it is clear that fn goes to f in L1, because the second term in the right hand side goes to 0. So integration fn mod of fn d mu goes to integration mod f d mu, that means fn goes to f in L1 as n goes to infinity. So for p equals to 1, again if part is also relatively simple. Now the main part of this entire proof is for p greater than 1. So the one interesting thing, one very important thing that we should point out, that there might be some problems where p equals to 1 and p greater than 1, they cannot be proved probably exactly in the similar fashion. We might need few more facts or interesting results to prove for p greater than 1. So, but the only problem here is that the above proof which we have just done for p equals to 1, it's very difficult to generalize that result. Just what we have said, what I have said, that it's very difficult to generalize that result when p greater than 1. So what we do, but first let us see what we do. We are trying to prove for p equals to 1, and let's see how we can prove it, if possible in a different way. But again, triangle inequality is very important in this case. So apply triangle inequality, we can immediately get, right, mod of fn minus f less than equals to mod fn plus mod f, which implies mod of fn plus mod f minus mod fn minus f, that is greater than or equals to 0. This part is relatively clear. Now we apply Fattoush Lemma. So after a long time we are going to apply Fattoush Lemma. So what we have is twice integral mod f d mu equals to integration lim of mod fn plus mod f minus mod fn minus f. So actually we can always write this thing as 2f equals to 2f plus fn minus fn, or which is equals to fn plus f minus of fn minus f, and then we apply the triangle inequality so that we can write this thing immediately. And this quantity is less than equals to lim integration mod fn plus f minus mod fn minus f because of Fattoush Lemma. Now lim integration mod fn plus, which is equals to lim integration mod fn plus integration mod f, because there is no n, minus lim sup of mod of fn minus f. Now since this is converging, so we can write this quantity as twice integral mod of f minus lim sup of integral mod of fn minus f, which implies immediately that lim sup of integration mod of fn minus f is less than equals to 0, just from here, which immediately implies that since it is mod, so this should converge to 0. So integration mod of fn minus f, so it cannot be less than 0, so it must be 0. So that automatically implies that integration fn minus f goes to 0, that is fn converges to f in L1. So we have proved the same thing, but we have applied Fattoush Lemma. The proof is not really very extremely easy, but after applying if we can apply Fattoush Lemma after considering the triangle inequality, the proof is relatively similar again. But the beauty of this, it would be probably easy to extend this for p greater than 1. However, first note that consider another function phi x, which is mod of x to the power p on the entire real line R. Now since we have this mod of x to the power p function, and we can apply this as a kind of convex function, so we can apply Jensen's inequality to get modulus of fn minus f by 2 whole to the power p equals to modulus of fn, we can write minus f as plus of minus f by 2 whole to the power p, and apply Jensen's inequality, we can get less than equals to mod of fn to the power p plus mod of minus f to the power p by 2. This is important, which is equals to mod of fn to the power p plus mod of f to the power p by 2. Now multiplying both sides by 2 to the power p, we have 2 to the power p minus 1 mod of fn to the power p plus 2 to the power p minus 1 mod of f to the power p minus mod of fn minus f to the power p greater than equals to 0. Now we have exactly the same kind of inequality that we got in case of when we discussed p equals to 1. Almost exactly the same, but there is a constant factor to the power p minus 1 and there is a to the power p. All these things are there, but more or less a similar form we got. So now we have to apply Fattoush Lemma as in the proof of the case when p equals to 1. Just application of Fattoush Lemma, we'll be able to prove this result completely. So we have seen that we have proved this p equals to 1 first in a very simple way, but that cannot be generalized to general p when p greater than 1. So we have given an alternative proof using Fattoush Lemma when p equals to 1, and this just one application of Jensen's inequality considering a function mod of x to the power p. We get similar kind of inequality, and then we are in a position to apply Fattoush Lemma, from which we can get the complete proof very easily. So we have seen a very interesting way one problem where we first checked whether what is the nature of the integrand as n goes to infinity or k goes to infinity, depending on whether it is a function of k and n. It doesn't really matter. But first we checked what is the property of the integrand, that the function inside the integral, which is a sequence of functions. And then we see whether it satisfies the condition of monotone convergence theorem or Lebesgue-dominated convergence theorem, and accordingly we have applied that theorem in order to finally get the limit of the integral, that means the ultimate limit. So the entire procedure is very simple, not at all difficult. Only thing we need to be very careful about checking the conditions of the respective theorems. We have also seen another example relating to LP convergence, of course based on another measurable function, but this is a very typical problem. And so today we have applied a few known theorems, mostly monotone convergence theorems and Lebesgue-dominated convergence theorems, and of course that will help us to know some kind of convergence of measurable functions. So just note that again the techniques or the elegance with which we have solved these problems just by application of two very important theorems, which we have studied theoretically, but this actually opens an area where we can apply these theorems. So in any other field in mathematics or statistics or in such, whenever we encounter this kind of integrals, we can think of to evaluate the value of this integral. If we can write this as a sequence of integrals or functions, we can think of applying these theorems in order to get the final limits.